This is the first in our series of lectures on rational expressions or rational functions. And whenever you're starting a new math topic, it's a good idea to start with some definitions. And I've got the definition here for a rational expression. And it's a fancy math sounding kind of thing. But really all a rational expression is it's a special kind of fraction. It's a fraction where the numerator and denominator are both polynomials. For example, 4x plus 1 over 3x minus 2. That's a rational expression. If you want to turn this into a function, we could use our function notation and stick an f of x in front of it. And these polynomials can get as big and as complicated as you like for them to be, as we need them to be. And they can also be relatively simple. For example, 1 over x is a rational expression. That 1 in the top meets the technical definition of a polynomial. So yeah, that's going to count. Also, we can flip this over. We can do something like x over 1, which is just x. Okay, that is also a rational expression. You kind of see a similar behavior here to what we see between the integers and the rational numbers. Every polynomial is also a rational expression, just like we can think of the integer 3 as a fraction by putting it over 1. You know, we sometimes really do that. For example, if we're trying to add it to another fraction and we need to give them a common denominator, just by the same argument, we can take any polynomial and turn it in and make it meet this definition by putting it over 1. All right, so technically, regular polynomials meet this definition of a rational expression. But for our purposes, for purposes of kind of this new material we're going to be looking at, we're really going to kind of limit our attention to the more interesting case where there is actually a variable in the denominator. All right, so the one other thing I want you to focus on here is this q not equal to 0 part. Look over here at the definition. Q is the polynomial in the denominator. And again, if you think back, we're going to be drawing a lot of analogies just to regular numeric fractions as we go through our series of lectures here. When we're talking about numeric fractions, remember the denominator of a fraction is never allowed to be 0. You're not allowed to divide by 0. Oh, we still have that same restriction here. Right? We're always going to limit that polynomial that we put in the denominator to only have values where it's not equal to 0. So let's take a look at this guy. This is, again, a very simple polynomial. And I want to think about how we can evaluate this. That's why I wrote this using our function notation. So for example, if I wanted to calculate f of 0, that would be 1 over 0 minus 1, which is just negative 1. Right, similarly, I'll try another one here. F of 2 is 1 over 2 minus 1, which is positive 1. So here we can kind of actually substitute values in, just like we could do with polynomials, and evaluate these rational expressions for specific values. Now, I want to try one more number here, and it's going to be a bad one. Right? What happens if we try to evaluate f of 1? Right? Well, that's 1 over 1 minus 1, which is 1. Whoa, sorry about that. Which is 1 over 0. And that's not allowed. Right? We are not allowed to divide by 0 with these rational expressions any more than we could with regular numeric fractions. So, this is what that q not equal to 0 part is talking about. This rational expression, 1 over x minus 1, doesn't exist when x equals 1 because if we substitute 1 for x, the denominator becomes 0. And we have a word for this. We have a name for this situation. These values that make the denominator equal to 0, those are the values where the rational expression is undefined. So we have a question like this, for what values of x is this specific expression undefined? What that's asking is, in practical terms, what we're looking for is, what values of x make the denominator equal to 0? And we know how to find those. I'm going to take the denominator, x squared minus 8x plus 15, and set that equal to 0. Right? When the denominator is equal to 0, the expression is undefined. So now I need to solve this equation. Let's see, I can factor this. This is x minus 3 times x minus 5. And this gets us two answers. I'm going to set x minus 3 equal to 0. That tells me that the rational expression is undefined at 3. And I'm going to set x minus 5 equal to 0. And this tells me that the rational expression is undefined also at 5. And you can check this real quickly. Right, you can check this real quickly. Put 3 into the denominator for x. Put 5 into the denominator for x. Both times you're going to get 0, and that's not allowed. All right, so let's take a look at this guy. Right, let's see what's happening here. And I want to go ahead and pause the presentation for a second. Right, try doing this yourself. See what you come up with. Then you come back and we'll walk through it together. So what I'm going to do here, I'm going to set the denominator equal to 0. And I got to solve this equation. Well, I got my fingers crossed here. I'm hoping this thing factors. Let's see. I'm thinking 3x plus 1x minus 1 equals 0. And that's going to give me two results again. 3x plus 1 equals 0. That's 3x equals negative 1. X equals negative 1/3. And over here on this side, whoops, x minus 1 equals 0. That gets me x equals 1. So again, quadratic polynomial in the denominator. And I got two values where this expression is undefined. What's next on our agenda? Well, now that we know what rational expressions are and kind of some basic concepts of how to work with them, our next step is going to be to kind of follow the same path that you followed when you were learning about numeric fractions. First, you learn what they are, and the second thing you learn is how to simplify them. And that's where we're going to go in the next lecture in the series.